Sairam, in this video, we are going to see how to prove n to the power 4 plus 4 is a composite number whenever n is greater than 1 and also n by phi of n is equals to summation d divides n mu square d divided by phi of d. First, we'll prove that n to the power 4 plus 4 is a composite number whenever n is greater than 1. Before going to the proof, we'll take certain values of n and check whether the statement is true or not. What happens if n is equals to 1? If n is equals to 1, then this n to the power 4 plus 4 is going to be 5, where 5 is a prime number. If n is equals to 2, then 2 to the power 4 plus 4 is going to be 20, where 20 doesn't belong to prime number. It is a composite number. Similarly, if n is equals to 3, then it is going to be 81, where 81 is also a composite number. Therefore, we can clearly observe that n to the power 4 plus 4 is a composite number whenever n is greater than 1. Let's prove it. We will prove the above statement by taking two cases. First, consider n to the power 4 plus 4 as an equation 1. Case 1, if n is even, that is, we can write n as 2k. Then the equation 1 becomes, that is, substituting n value in the equation 1, we are going to get 16k plus 4, which is an even number and it is clearly divisible by 4. Therefore, we can say that n to the power 4 plus 4 is a composite number whenever n is even. Case 2, if n is odd, equation 1 can be written as n to the power 4 plus 4n square minus 4n square. Just adding and subtracting 4n square to equation 1. N to the power 4 plus 4n square is of the form a plus b the whole square. Therefore, we can write it as n square plus 2 the whole square minus 4n square is equals to 2n square. It is again of the form a square minus b square. Therefore, we can write it as n square plus 2 minus 2n into n square plus 2 plus 2n. N square plus 2 minus 2n, again we can write it as n minus 1 the whole square plus 1, which is greater than 1. Similarly, n square plus 2 plus 2n is equals to n plus 1 the whole square plus 1, which is greater than 1. The product of these two factors, that is n minus 1 whole square plus 1 into n plus 1 the whole square plus 1 is again going to be greater than 1. If n is odd, the above product is going to be an even integer. So let's check it whether it is true or not. Let's take n is equals to 5. And when we substitute 5 in the place of n in the equation, we'll get 5 minus 1 whole square plus 1 into 5 plus 1 the whole square plus 1, which is nothing but product of two integers, that is 17 and 37. The product of 17 and 37 is going to be 629. The 629 is clearly divisible by 37. Therefore, we can say that the product of two integers in this case is a composite number. Therefore, from case 1 and case 2, we can clearly conclude that n to the power 4 plus 4 is a composite number whenever n is greater than 1. Next, we'll prove that n by phi of n is equals to summation d divides n mu square d divided by phi of d. First, consider the RHS, that is summation d divides n mu square d divided by phi of d. This we can simplify. This we can write it as summation d divides n mu square d into summation d divides n 1 by phi of d. Let n is equals to product of P1, P2 and so on Pn. Here P1 into P2 into P3 and so on Pn are distinct primes. Since it is a distinct primes, the GCD of the two primes is going to be 1. Summation d divides n 1 by phi of d is equals to 1 by phi of p1 into phi of p2 and so on phi of pn. Phi of p1 whole inverse into phi of p2 whole inverse and so on phi of pn whole inverse. Call this as equation 1. Now we have phi of pi is equals to 1 minus 1 by pi, which is nothing but pi minus 1 divided by pi. Call this as equation 2. Using equation 2, we can write equation 1 as phi of d whole inverse is equals to p1 divided by p1 minus 1 into p2 divided by p2 minus 1 and so on pn divided by pn minus 1, which is equals to product of pi that divides n pi minus 1. Sorry, here is a mistake. It is not 1 minus pi, it is pi minus 1. Call this as equation 3. By known theorem, we have phi of n is equals to n into product of pi that divides n into 1 minus 1 by pi. When we do the cross multiplication, n by phi of n is equals to product of pi that divides n into 1 minus 1 by pi whole inverse. Product of pi divides n into 1 minus 1 by p of I whole inverse is nothing but product of p divides n into pi divided by pi minus 1. Call this as equation 4. From equation 3 we have summation d divides n 1 by phi of d is equals to product of p divides n p of I divided by p of I minus 1. From equation 3 and 4, we can write n by phi of n is equals to product of pi divides n into pi divided by pi minus 1, which is equals to summation d divides n 1 by phi of d. Let's consider equation A, that is summation d divides n mu square d into summation d divides n 1 by phi of d. Substituting n by phi of n in the place of summation d divides n 1 by phi of d will get summation d divides n mu square d into n by phi of n. Here mu should be square free number because mu of d square is always going to be 0 and we know that mu of d is always going to be 1 or minus 1. Therefore, squaring the mu will always be equal to 1. Therefore, summation d divides n mu square d divided by phi of d is equals to n by phi of n. With this, we got to know now how to prove n to the power 4 plus 4 is a composite number whenever n is greater than 1, and also we know how to prove n by phi of n is equals to summation d divides n mu square d divided by phi of d. Thank you one and all for watching this video.